Okay, here's our question. We're working on number 3 here. We've got this stone wall, and tells you the temperature that it reaches, presumably that's steady state, and it gives you the emissivity. And then it asks for the radiant heat transfer from the wall per square meter. So we're looking for something like, watts per meter squared. What's interesting, okay, it tells you at that temperature. It's interesting that you have to make a number of assumptions. So the first thing that we have to assume is, the wall is, I don't know, maybe up against a building, and so we're just looking at one way heat transfer from that wall. The other thing that it doesn't tell you about is anything about what about the radiant energy coming into the wall. So we're probably just looking at the radiant energy that's coming off of the wall and ignoring the things that are around. So let's go ahead and attempt that. So we're looking for basically the solution watts per meter squared, and it should be pretty straightforward. We know that this should equal to the area times sigma times epsilon times t to the fourth. So watts per meter squared, it's going to give us this value, sigma epsilon t to the fourth. So we just have a straightforward plug-in chug. The Stefan-Boltzmann constant being 10 to the 8th watts per meter squared, Kelvin to the 4th, times 0.90, times the absolute temperature, which is 60 plus 273 Kelvin to the 4th power. So let's just check our units here, make sure they work out. We have meters squared, watts per meter squared is what we want. Kelvin to the 4th with this Kelvin to the 4th, that should work out just fine. So I'm going to need a calculator for this. Oops. I got that Q dot over A of the wall is 627 watts per meter squared. About, well, I call that 630 watts per meter squared. Does that seem kind of reasonable? Let's see, 630 watts per meter squared. That's less than incoming solar radiation. That sounds about possible. That's possible.